The morning of December the 25th, 1944, dawned cold and grey over the Sauer River in Luxembourg. Private Heinrich Müller crouched in a frozen foxhole on the German side of the river, watching his breath turn to mist in the frigid air. Around him, 800 men from the Third Battalion, 18th Volksgrenadier Division, prepared to cross the icy water and establish a bridgehead on the opposite bank. They had been told the Americans were retreating, that one more push would break through to Antwerp and change the course of the war. Müller believed this because he had to, because the alternative was admitting that everything he had been promised about final victory was a lie. The battalion commander, Major Klaus Zimmermann, stood at the river's edge with his map case open, pointing across the water to the tree line where American positions were supposed to be thinly held. The plan was simple: cross the river under cover of morning fog, overwhelm the defenders with superior numbers, and advance 3 kilometers before nightfall. Müller checked his Mauser rifle one last time and looked at the faces of the men around him. Most were teenagers or men in their 40s, the last reserves Germany could scrape together after 5 years of war. They wore mismatched uniforms and carried ammunition pouches that were only half full, but they had been trained to believe that German discipline and fighting spirit could overcome any material disadvantage. What Private Müller did not know was that on the opposite bank, American artillery crews were loading shells marked with red bands and a code name he had never heard of, Posit. These shells contained a technology that German scientists had declared impossible to build, a miniature radar system packed into the nose of an artillery round that could survive being fired from a cannon and detonate automatically when it sensed a target below. In the next 20 minutes, Müller and 700 of his comrades would discover that courage and discipline meant nothing against a weapon that turned the sky itself into a killing field. This is the story of how American physicists created a device their enemies thought was impossible. How it remained secret for 3 years, while German and Japanese soldiers died without understanding what was killing them, and how on Christmas Day, 1944, it eliminated an entire German battalion in a single artillery barrage that rewrote the rules of warfare forever. The problem that led to the proximity fuse began not in Europe, but in the skies above Pearl Harbor on December the 7th, 1941. When Japanese aircraft attacked that morning, American anti-aircraft gunners fired thousands of shells equipped with mechanical time fuses. These fuses were supposed to detonate at specific altitudes, creating walls of shrapnel that enemy planes would fly through. The system required gunners to estimate an aircraft's altitude and speed, calculate the shell's time of flight, set the fuse manually, and hope everything worked correctly. It rarely did. Of the 48 civilians killed at Pearl Harbor that day, most died when improperly fused American shells exploded on impact with the ground in downtown Honolulu instead of in the air near their intended targets. The shells that did explode at altitude rarely hit anything. The statistics were grim. In the worst cases, during the early war period, gunners fired thousands of shells for every enemy aircraft destroyed. Even under good conditions, hitting a fast-moving aircraft at altitude with time-fused shells was nearly impossible. That was not a defensive weapon. That was a waste of ammunition and lives. The United States Navy understood they had a critical problem. Modern aircraft were too fast, too maneuverable, and flew at altitudes that made accurate time fusing nearly impossible. What gunners needed was a fuse that would automatically detonate when a shell came close to an enemy aircraft. A proximity fuse. The concept was not new. Multiple nations had explored the idea for years, but every attempt had failed because the engineering challenges seemed insurmountable. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. To work effectively, a proximity fuse needed to sense when it was near a target and detonate automatically. That meant incorporating some kind of electronic sensor into the nose of an artillery shell. But artillery shells experienced forces that destroyed conventional electronics instantly. When fired from a 5-inch naval gun, A shell accelerated to 2,800 feet per second in the length of the gun barrel. That created a setback force of 20,000 times the force of gravity, 20,000 G-forces. Simultaneously, the rifling grooves in the gun barrel spun the shell at 25,000 revolutions per minute to stabilize its flight. Any electronic components inside the shell would be subjected to crushing acceleration, violent rotation, and impact forces that would pulverize ordinary vacuum tubes into glass powder and metal fragments. Then there were the practical requirements. The fuse needed to be small enough to fit inside a standard artillery shell. It needed to be reliable enough for mass production. It needed safety mechanisms to prevent premature detonation that could kill friendly gun crews. It needed to be weatherproof, stable in storage for months, and cheap enough to manufacture by the millions. It needed to work in rain, in fog, at night, in tropical heat and Arctic cold. And it needed to be simple enough that ordinary sailors could handle it safely without specialized training. German scientists had been working on proximity fuses since the early 1930s. By 1944, they had explored more than 30 different designs, including acoustic fuses, triggered by engine sounds, electrostatic field detection, and radio frequency systems. None worked reliably. In 1943, German engineers reached a definitive conclusion. Building a vacuum tube-based radio fuse for artillery shells was technologically impossible. The acceleration forces would destroy the tubes. The problem could not be solved with existing technology. British scientists reached a different conclusion. Starting in 1939, researchers at Pi Limited began developing ruggedized vacuum tubes that could withstand high acceleration. By 1940, they had working prototypes of proximity fuses for unrotated projectiles, the British cover name for solid-fueled rockets. Rockets had relatively gentle acceleration compared to artillery shells, so the electronic components faced less stress. The British fuses worked adequately in rockets, but attempts to adapt them for high-velocity artillery consistently failed. The tubes shattered, the circuits failed, the fuses were unreliable. In August 1940, a British technical mission led by Henry Tizard arrived in the United States, carrying a black metal deed box containing Britain's most secret military technologies. Among the items in that box were circuit diagrams and prototypes of British proximity fuse designs. The British hoped American industry could solve the manufacturing problems they could not overcome alone. The National Defense Research Committee assigned the proximity fuse project to Section T of the Department of Terrestrial Magnetism at the Carnegie Institution in Washington. Section T was led by Dr. Merle Tuve, a physicist who had helped develop the theoretical foundations for radar in the 1920s. Tuve understood that the core technical challenge was not the concept, but the execution. Radio proximity fuses were conceptually simple. A miniature transmitter in the nose of the shell would emit radio waves. When those waves reflected off a nearby target, a receiver circuit would detect the reflected signal and trigger a detonator. Simple concept. Extraordinarily difficult engineering. Tuve assembled a team of physicists and engineers and gave them an impossible deadline. The Navy needed working proximity fuses for 5-inch anti-aircraft guns as soon as possible. Japanese air power was destroying American ships. Without an effective anti-aircraft defense, the Navy could not operate in the Pacific. Tuve's team had months, not years, to solve problems that had stumped British and German scientists for a decade. The team included some of the brightest minds in American physics and engineering. Richard Roberts and Henry Porter conducted experiments on circuit designs. Robert Broad worked on receiver sensitivity. Harry Diamond and Wilbur Hinman from the National Bureau of Standards developed fuse designs for rockets and bombs. The collaboration brought together academic researchers, government scientists, and industrial engineers in ways that had never been attempted before. Every member understood they were racing against time. American sailors were dying in the Pacific while they worked. The first breakthrough came from Lloyd Berkner, one of Tuve's engineers. Berkner developed a system using separate transmitter and receiver circuits instead of a combined transceiver. This simplified the electronics and made the system more reliable. But the vacuum tube problem remained unsolved. Standard vacuum tubes shattered under the acceleration forces of gunfire. The glass envelopes cracked, the filaments broke. The tube elements came loose and destroyed the circuits. The solution came from Western Electric Company and Raytheon. These companies manufactured miniature vacuum tubes for hearing aids. Hearing aid tubes were already ruggedized for portable use. They were small, mechanically robust, and used relatively little power. Working with TÜV's specifications, Western Electric and Raytheon engineers modified hearing aid tube designs to survive artillery gun firing. They reinforced the glass envelopes. They redesigned the filament mounts. They tested the tubes by firing them from air cannons into solid blocks of wood, subjecting them to acceleration forces far exceeding what they would experience in actual combat. Most tubes failed. The engineers redesigned them, tested again, failed again, redesigned again. By January 1942, after months of iterative testing and redesign, they had vacuum tubes that survived 20,000 G-forces and 25,000 RPM spin rates. The tubes were tiny, barely larger than a rifle cartridge. Each proximity fuse required 5 of these miniature tubes, along with resistors, capacitors, a battery, a safety mechanism, and a detonator, all packed into a space smaller than a beer can and weighing less than 2 pounds. The battery system alone presented enormous challenges. Standard batteries could not withstand the firing shock. Engineers developed a reserve battery that was activated by the setback force of firing. A small glass ampule containing electrolyte would shatter when the shell was fired, activating the battery. The safety mechanisms required equally innovative solutions. The fuse needed to remain completely inert during handling, transportation, and loading. It could not arm until the shell had traveled far enough from the gun to protect friendly forces. Engineers designed a complex system using mercury switches that required centrifugal force from the shell's rotation to close, combined with a timer that ensured at least 3/10 of a second elapsed after firing before the fuse could detonate. This meant the shell had to travel at least 750 feet from the gun before it became active. Even if a shell misfired and fell near the gun crew, it would remain harmless. In early August 1942, the Navy conducted the first live fire test of proximity fuse shells in the Chesapeake Bay. The cruiser, USS Cleveland, fired at radio-controlled drone aircraft on August 12th during its shakedown cruise. The test was scheduled for 2 days. It ended after 1 day because all the drones were destroyed. The gun crews aboard Cleveland fired 4 shells. 3 drones were destroyed. Navy observers present at the test were astonished by the results. The proximity fuses worked perfectly. For the first time in history, anti-aircraft gunners could reliably hit moving aerial targets without direct hits. The shells just needed to pass within 70 feet of the target, and the proximity fuse would detonate automatically, shredding the target with shrapnel. The improvement over time-fuse shells was so dramatic that some Navy officers initially suspected the test had been rigged or that the results were somehow misleading. But subsequent tests confirmed the initial findings. The proximity fuse represented a genuine breakthrough in anti-aircraft warfare. But successful testing and combat deployment were very different things. TÜV's team needed to scale up from prototype production to mass manufacturing. By January 1943, Section T had moved from the Carnegie Institution to a much larger facility and been reorganized as the Applied Physics Laboratory under Johns Hopkins University, with TÜV as director. The project now involved 26 contractors and 10,000 workers. More than 100 American companies contributed to proximity fuse production, including General Electric, RCA, Raytheon, Sylvania, Westinghouse, Eastman Kodak, Zenith, Philco, and even Wurlitzer, the organ manufacturer. Each proximity fuse contained 130 miniaturized electronic components. Assembly required precision work. Workers at factories across America built these fuses without knowing what they were building. Security was absolute. The project had the same classification level as the Manhattan Project developing the atomic bomb. Workers who asked what the fuses were for were told only that they were critical to winning the war. Many workers never learned the truth until after the war ended. The Crosley Corporation in Cincinnati, Ohio, became one of the largest proximity fuse manufacturers, producing 5.2 million units, roughly 24% of total wartime production. The company converted its barrel organ factory into a fuse assembly line. General Electric's Christmas tree lamp factory in Cleveland was retooled to produce miniature vacuum tubes. Eastman Kodak, RCA, and Sylvania joined the production effort. At peak production, American factories were manufacturing more than 100,000 proximity fuses per week. The fuses that cost $732 each in early 1942 cost just $18 each by 1945. That price reduction reflected both improved manufacturing efficiency and the economies of scale that only American industry could achieve. In November 1942, the Navy shipped 5,000 proximity fuses to Pearl Harbor. The Pacific Fleet received 4,500 of them and began distributing them to ships operating in the Solomon Islands. But the fuses came with strict restrictions. They could only be used over open water where dud shells would sink to the ocean floor. If a fuse failed to detonate and fell on land, Japanese engineers might recover it and reverse engineer the technology. That risk was considered unacceptable. On January 5, 1943, those restrictions were put to the test. The light cruiser USS Helena was operating off Cape Hunter on the south coast of Guadalcanal when Japanese dive bombers attacked. After dropping their bombs, the aircraft pulled up and began climbing away. Lieutenant Red Cochran commanded Helena's aft 5-inch battery. He ordered his gun crews to fire 3 salvos with proximity fuse shells at the departing aircraft. The gun crews had minimal time to aim. The aircraft was already several thousand feet away and climbing fast. All 3 shells exploded in the air near the dive bomber. The aircraft disintegrated and fell into the ocean. Helena's crew had achieved the first confirmed kill of an enemy aircraft using a proximity fuse shell in combat. It was not a lucky hit. It was repeatable technology. Over the next 12 months, the effectiveness of proximity fuses in naval combat became undeniable. In 1943, Navy ships fired 9,128 proximity-fused rounds and destroyed 61 enemy aircraft. That was 1 kill for every 155 shells fired. The old-time fuse shells required 508 rounds per kill. The proximity fuse was more than 3 times as effective. And this was just the beginning. As gun crews gained experience with the new fuses and fire control systems improved, the kill ratios got even better. By 1944, the number of proximity fused rounds fired climbed to 32,826, accounting for hundreds of aircraft destroyed. During the Marianas Campaign, proximity fused 5-inch shells provided critical air defense for carrier task forces operating deep in Japanese-controlled waters. During the Battle of the Philippine Sea in June 1944, American ships equipped with proximity fuses shot down numerous Japanese aircraft attempting to attack the carriers. The Japanese naval aviators, among the most experienced in their fleet, found themselves unable to penetrate the defensive screen created by proximity-fused anti-aircraft fire. One Navy study concluded that for every enemy plane destroyed, 5-inch guns had previously needed to fire approximately 1,000 time-fused shells. With proximity fuses, that number dropped to about 250 shells per kill, a 4-fold improvement in effectiveness. On May 11, 1945, the destroyer USS Hugh W. Hadley was on radar picket duty off Okinawa when more than 100 Japanese aircraft attacked in a coordinated strike. Hadley's 5-inch guns were equipped with proximity fuses. In 90 minutes of continuous combat, Hadley shot down 23 aircraft, setting an all-time U.S. Navy record for a single engagement. Every proximity fuse shell that came within 70 feet of a target detonated automatically, filling the sky with lethal shrapnel patterns that aircraft could not avoid. The nearby destroyer USS Evans accounted for 19 additional aircraft before being forced to retire. Together, The two destroyers shot down more than 40 enemy aircraft. Both ships received Presidential Unit citations for this action. The after-action report described the proximity fuse as indispensable. But while the Navy was using proximity fuses extensively in the Pacific, the Army was prohibited from using them overland in Europe. The restriction remained in place through 1943 and most of 1944. Army artillery officers knew proximity fuses existed. They had heard reports from the Pacific. They knew the technology worked. But Pentagon officials feared that even a single dud shell falling into German hands could compromise Allied air superiority. Germany had the most advanced scientific establishment of any Axis power. If German engineers reverse-engineered the proximity fuse, they might develop countermeasures that could blind Allied radar or create their own proximity-fused anti-aircraft shells that would devastate Allied bomber formations over Germany. The risk seemed too great. That calculation changed on June 12, 1944. Germany began launching V-1 cruise missiles at London. The V-1s were jet-propelled flying bombs, pilotless aircraft packed with explosives and aimed at civilian targets. They flew low and fast, approaching speeds of 400 miles per hour. They were extremely difficult to intercept. Traditional anti-aircraft guns could rarely hit them because the V-1s were too small and too fast for accurate time fusing. British fighter pilots tried to shoot them down or tip their wings to send them off course, but it was dangerous work, and many pilots died attempting it. The V-1s killed tens of thousands of civilians and caused massive damage to London. The Pentagon authorized limited use of proximity fuses to defend London against the V-1 attacks on June 12, 1944. Initially, the fuses were restricted to 90mm anti-aircraft guns and British 3.7-inch guns positioned along the English coast where dud shells would fall into the ocean. The results were immediate and dramatic. In the first week of operations, British anti-aircraft guns destroyed 17% of incoming V-1s. This was already better than the 24% success rate achieved with traditional methods, including fighter interceptions and anti-aircraft fire combined. But as gun crews gained experience with the new fuses and fire control radars improved, the success rate climbed steadily. By the end of the fourth week, proximity fused shells were accounting for 79% of all V-1s destroyed by anti-aircraft fire. By late August, after proximity fuses were widely deployed across the entire defensive belt, that percentage reached 74% of all incoming missiles. On some days, it reached 82%. The Germans launched 9,300 V-1s at England between June and August. Without proximity fuses, the casualties and destruction would have been catastrophic. The proximity fuse had saved London from what could have been an even more devastating assault. British Prime Minister Winston Churchill later called the proximity fuse potent against the small unmanned aircraft and credited it with preventing far greater loss of life. When V-1 attacks shifted to the port of Antwerp in September 1944, the restrictions on proximity fuse use over land loosened further. Antwerp was critical for supplying Allied armies advancing into Germany. Losing the port would cripple the Allied offensive. The Germans recognized Antwerp's strategic importance and redirected their remaining V-1 launchers to target the city and port facilities. Between October 1944 and March 1945, the Germans launched more than 8,000 V-1s at Antwerp. British and American anti-aircraft units established defensive belts around the city. The British 11th Armoured Division, defending Antwerp, came under a particularly intense barrage in September that required emergency modifications to anti-aircraft fuses. The Crosley Corporation in Cincinnati worked around the clock to produce the specialized fuses needed. British Prime Minister Winston Churchill authorized a special flight of Lancaster bombers to transport the fuses from Cincinnati to Europe, demonstrating the critical importance attached to maintaining Antwerp's defenses. Once the modified proximity fuses were deployed, a single anti-aircraft unit in Antwerp destroyed 48 of the first 75 V-1s they encountered, a 64% success rate. With the V1 threat largely mitigated, the port of Antwerp remained open for the duration of the war. By the end of the campaign, anti-aircraft units equipped with proximity fuses had destroyed more than 2,000 V1s, targeting Antwerp and London combined. On October the 25th, 1944, the combined Chiefs of Staff authorized general use of proximity fuses over land for anti-aircraft defense, formalizing what had become standard practice across the European theater. But ground artillery still could not use proximity fuses against enemy troops. Army artillery officers were furious. They knew proximity fuses would be devastatingly effective against ground targets. A conventional artillery shell detonated on impact with the ground, which meant that troops in trenches, foxholes, or behind cover were protected. But a shell that detonated in the air above them would spray shrapnel downward into their positions. Trenches became death traps. Foxholes offered no safety. Even log-reinforced bunkers could be penetrated by high-velocity fragments. Proximity-fused artillery would multiply the lethality of American firepower many times over. But the Pentagon held firm. The risk of a dud shell falling into German hands was still considered too high. Army artillery would have to wait. Then, at 05:30, on December 16th, 1944, Germany launched Operation Wacht am Rhein. 3 German armies attacked through the Ardennes forest in Belgium and Luxembourg, hitting thinly held American positions with overwhelming force. The attack achieved complete surprise. German armor punched through American lines and began driving west toward the Mauser River and the Belgian port of Antwerp. The Battle of the Bulge had begun, and American forces were in serious trouble. Colonel Oscar Alfred Axelson stood in the fire direction center of the 406th Field Artillery Group near Monschau, Germany, listening to panicked radio calls from the 38th Cavalry Squadron. The lightly armed cavalry troopers were being overrun by German infantry. They needed artillery support immediately, or they would be annihilated. Axelson had exactly what they needed. Sitting in ammunition storage bunkers behind his position were crates of brand-new artillery shells marked with red bands and the code name POSIT. These shells contained the revolutionary fuse that could detonate in mid-air above enemy troops, turning near misses into kills. But there was one massive problem. Supreme Commander Dwight Eisenhower had not authorized their use. The Pentagon had classified these fuses at the same level as the atomic bomb. The fear was that if a dud shell fell into German hands, enemy engineers might reverse engineer the technology or develop countermeasures that could threaten Allied air superiority. Using them without authorization could result in a court-martial. Axelson made his decision in seconds. The cavalry squadron was dying. Regulations could wait. He ordered his gun crews to load the proximity-fused shells and open fire. Minutes later, the first POSIT rounds screamed over German positions and detonated 30 feet above the ground. The German infantry advancing on the 38th Cavalry Squadron suddenly found themselves engulfed in a steel rain of shrapnel falling from above. Foxholes offered no protection. Log-reinforced bunkers were penetrated by fragments. Men who had felt safe in covered positions were cut down by explosions they could not see coming. The German attack stalled immediately. What Colonel Axelson did not know was that he had just fired the first land-based proximity-fused artillery shells in the European theater. And what the Germans being killed by those shells did not know was that they were facing a weapon their best scientists had declared impossible to build. 3 days later, on December 19th, General Dwight Eisenhower formally requested authorization to use proximity-fused artillery shells across the entire European theater. The German offensive was the largest attack the US Army had ever faced. Every advantage mattered. On December 21st, all restrictions were lifted. Proximity-fused artillery shells were released for general use. The timing was critical. SS Colonel Otto Skorzény's troops were attacking the town of Malmedy. American artillery battalions supporting Malmedy fired proximity fuses with devastating effect. The attacking German soldiers found themselves caught in airbursts that detonated overhead with no warning. Some Germans charged directly into the artillery fire, hands raised, screaming, "Kamerad," the German word for comrade, trying to surrender. By December 23rd, estimates suggested as many as 2,000 German soldiers had been killed by proximity-fused artillery shells in just the first few days of their use. The Germans quickly realized they were facing a new type of weapon. Prisoners of war repeatedly described the demoralizing effect of artillery shells that exploded in the air above them with perfect timing. Traditional artillery gave soldiers a brief moment of hope. They would hear the whistle of incoming shells and dive for cover. If they were in a trench or foxhole, they might survive even a direct hit nearby, because the explosion was on the surface. But proximity-fused shells detonated 30 to 50 feet in the air directly above defensive positions. There was no cover. There was no warning. The shells arrived silently at high velocity and detonated overhead, raining shrapnel straight down. Soldiers who had felt safe in prepared defensive positions were being killed without ever seeing the threat. The psychological impact was severe. German commanders offered rewards for any soldier who could recover an intact proximity fuse. They needed to understand how the weapon worked so they could develop countermeasures or copy the technology. In late December 1944, German forces captured an American ammunition dump that contained 20,000 proximity-fused artillery shells. German engineers examined the fuses carefully. They recognized sophisticated electronics were involved, but they could not understand how the technology worked. Most critically, German engineers could not believe that miniature vacuum tubes could survive the acceleration forces of artillery gun firing. Their own research had convinced them such tubes were impossible to manufacture. They assumed the captured fuses were defective or designed for a different application. They never realized what they were looking at. By the time German scientists understood the significance of proximity fuses, the war was nearly over, and Germany had no industrial capacity left to develop. Countermeasures. On the night of December 25th and 26th, 1944, General George Patton's Third Army caught a German battalion attempting to cross the Sauer River near Echternach, Luxembourg. Private Heinrich Müller stood waist-deep in the freezing water, his rifle held above his head as he struggled against the current. Around him, 800 men from his battalion splashed through the darkness, trying to maintain formation as they crossed. The opposite bank was less than 100 yards away. American positions were supposed to be lightly held. Intelligence reports had promised that one more push would break through the enemy lines. Major Zimmermann urged his men forward from the riverbank, his voice carrying across the water despite the rushing current. The plan had seemed simple during the briefing: cross under cover of darkness, establish a bridgehead, and advance before dawn. German forces had been pushing American lines for 10 days since the Ardennes offensive began. Momentum was everything. One more successful crossing could open a gap that armor could exploit. What Zimmermann did not know was that American forward observers had spotted the German concentration hours earlier. Artillery batteries from the 318th Field Artillery Battalion had already calculated firing solutions for the river crossing site. Gun crews had loaded shells marked with red bands, posit rounds, proximity fuses. The crews had been waiting for German forces to commit fully to the crossing, to reach the point where retreat would be as dangerous as advancing forward. Müller felt the riverbed beneath his boots give way to deeper water. He pushed forward, following the man ahead of him, trying not to think about how exposed they were in the middle of the river. The cold bit through his uniform, numbing his legs and making each step an effort. Behind him, he could hear other soldiers struggling with the current, some losing their footing and being swept downstream before comrades pulled them back. The opposite bank looked impossibly far away in the darkness. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. On the American side of the river, Fire Direction Center officers gave the command to fire. Artillery crews 3 miles behind the front lines pulled lanyards almost simultaneously. Dozens of 105mm howitzers roared, sending proximity-fused shells arcing through the night sky toward the Sauer River. The shells climbed to their apex and began descending toward the coordinates where 800 German soldiers were caught in the middle of a river crossing with nowhere to hide. The first shells arrived 30 seconds after firing. They did not impact the ground or the water. Instead, at precisely 30 feet above the river surface, the proximity fuses detected the mass of men below and triggered their detonators. The shells exploded in a synchronized pattern that covered the entire crossing site, transforming the night into a brief flash of light and steel. Müller never heard the shells coming. One moment he was struggling through chest-deep water, and the next moment the air above him erupted. Hot shrapnel tore through the battalion like an invisible scythe. Men disappeared beneath the surface without a sound. Others screamed as fragments ripped through their bodies. The water around Müller turned red in the darkness. He felt something strike his shoulder, spinning him sideways, and then he was underwater, the current pulling him downstream while explosions continued overhead. The second volley arrived 8 seconds after the first. American artillery crews were firing for effect now, adjusting their aim to cover the riverbanks where German soldiers tried to reach safety. The proximity fuses detonated with mechanical precision, creating overlapping zones of destruction that no one could survive. Soldiers who had made it to the opposite bank found no cover from airbursts that rained shrapnel straight down. Those still in the water had nowhere to hide as fragments churned the surface. Major Zimmermann watched from the German side of the river as his battalion was annihilated. He had seen artillery barrages before. He had survived Russian artillery on the Eastern Front, where shells fell like rain and turned entire landscapes into moonscapes of craters and torn earth. But those shells had exploded on impact, creating danger zones that soldiers could avoid by taking cover in holes or behind obstacles. This was different. These shells were exploding in the air above his men with perfect timing, as if some unseen intelligence was positioning each detonation for maximum effect. The barrage lasted 3 minutes. American artillery crews fired 147 proximity fused shells at the river crossing site, each shell detonating at the optimal height to spray shrapnel downward across the maximum possible area. When the guns finally fell silent, the only sounds were the rushing water and the occasional cry from wounded men trapped on the riverbanks or floating downstream in the current. General Patton received the casualty report the following morning while reviewing operations at his command post. American burial details had crossed the river at dawn to count German dead and search for intelligence materials. They found bodies scattered along both banks and in the shallow water where the current had deposited them. The count was methodical and precise. 702 confirmed German dead, 43 wounded survivors who were captured, 11 men who managed to escape back to German lines, an entire battalion effectively destroyed in 3 minutes of artillery fire. Patton immediately wrote a letter to the War Department describing what had happened. His words were direct and unambiguous. The new shell with the funny use is devastating. We caught a German battalion which was trying to get across the Sauer River with a battalion concentration and killed by actual count 702. I think that when all armies get this shell, we will have to devise some new method of warfare. I am glad that you all thought of it first. 702 confirmed dead in a single artillery barrage. That was unprecedented lethality. Conventional artillery shells might have killed 50 or 60 soldiers under similar circumstances, maybe 75 if the timing and placement were perfect. The proximity fuse had multiplied the effectiveness of American artillery by more than 10 times. And this was not an isolated incident. Throughout the Battle of the Bulge, proximity-fused artillery devastated German formations caught in the open. In the Hürtgen forest, an American chief ordnance officer reported finding 96 bodies from a German patrol hit by a massed proximity-fused artillery barrage. The bodies looked as if they had gone through a meat grinder, he wrote in his report. The high-velocity shells arrived too quickly for German soldiers to hear them coming. The air bursts detonated with no warning. Foxholes provided no protection. The shrapnel even penetrated log-reinforced bunkers that would have stopped conventional artillery. German units that tried to advance through artillery fire were annihilated. German commanders reported that their soldiers were refusing orders to move forward because they knew proximity-fused artillery could kill them even in covered positions. Prisoners of war interviewed after capture described being in a dazed state after surviving proximity-fused barrages. They realized they were facing a new kind of artillery, but could not understand how it worked or how to evade it. Minor mutinies broke out among German units that were ordered into areas known to be covered by American artillery. Some German soldiers simply refused to leave their bunkers when proximity-fused artillery was falling. The Germans had felt safe from traditional timed artillery because heavy overcast weather prevented accurate aerial observation. American forward observers could not see German positions clearly, which meant timed artillery shells would be set based on estimates that were often inaccurate. German troops had learned to take cover whenever they heard artillery fire and wait for the barrage to end. But proximity-fused shells did not require accurate observation. The fuses automatically detonated at the optimal height above ground, regardless of weather conditions or visibility. American gunners just needed to know the approximate location of German forces and fire. The proximity fuses did the rest. The bad weather that had protected German forces now meant nothing. By late January 1945, German resistance in the Ardennes had collapsed. The Battle of the Bulge was over. American forces had stopped the largest German offensive of the war and were preparing to cross the Rhine River into Germany. Proximity-fused artillery had played a critical role in that victory. Patton later stated that the funny fuse won the Battle of the Bulge for us. While that was an overstatement, the proximity fuse had undeniably changed the tactical situation. German forces that would have been able to defend prepared positions effectively against conventional artillery were wiped out by airbursts they could not avoid. In the Pacific theater, the proximity fuse had an even more dramatic impact. By 1945, Japanese forces had adopted kamikaze tactics, using suicide aircraft loaded with explosives to attack American ships. These attacks were extremely difficult to defend against because conventional anti-aircraft fire required direct hits on aircraft that were deliberately trying to crash into ships at close range. Kamikaze pilots often approached at wave-top altitude, making visual detection difficult. They would then pull up sharply for their final dive, giving gunners only seconds to engage. But proximity-fused shells created a defensive barrier around ships that was almost impossible for kamikaze aircraft to penetrate. The shells did not require direct hits. A near miss was as lethal as a direct hit. Navy studies showed that ships using proximity-fused ammunition were 5 to 10 times more effective at stopping kamikaze attacks than ships using conventional time-fused shells. Ships equipped with 5-inch 38 caliber guns firing proximity-fused ammunition could create a lethal zone extending thousands of yards from the ship. Any aircraft entering that zone faced a statistical probability of destruction that approached certainty. Admiral R. Lee Burke, who commanded destroyers in the Solomon Islands campaign in 1942 and 1943, later wrote about the difficulties of defending against Japanese air attacks, especially after dark. Mechanical time fuses, which we had been using, only brought down a plane at night, by accident, he recalled it. They were good for harassing enemy aircraft at night, but that was about all. The proximity fuse changed everything by making nighttime air defense genuinely effective for the first time. In the 7 months from January to July 1945, American ships expended nearly 2/3 of all proximity fuses used during the entire war, shooting down more than 200 aircraft. The proximity fuse allowed the Navy to maintain operations in waters where kamikaze attacks would otherwise have made naval operations suicidally dangerous. The effectiveness of proximity fuses went beyond simple statistics. The psychological impact on enemy forces was significant. Japanese pilots knew that approaching American ships equipped with proximity-fused anti-aircraft guns meant flying into an invisible sphere of death. The shells did not need to hit them directly. They just needed to pass nearby and detonate. There was no way to evade this defense. Japanese pilots reported feeling helpless against weapons that seemed to anticipate their maneuvers. Some historians have suggested that the proximity fuse was one factor that pushed Japan toward kamikaze tactics. If conventional attack methods could not penetrate American defenses, suicide attacks might be the only option. The proximity fuse demonstrated a pattern that would repeat throughout World War II and beyond. Technological advantage in warfare does not come primarily from theoretical breakthroughs. It comes from engineering, execution, and manufacturing scale. The concept of a proximity fuse was well understood by multiple nations before the war began. What separated success from failure was the ability to solve thousands of small engineering problems, manufacture components to precise tolerances, and produce complex electronic devices in quantities of millions while maintaining quality control. The United States had the industrial base, the skilled workforce, and the organizational structure that could coordinate work across dozens of contractors. Germany and Japan did not. By 1944, American industry was producing more proximity fuses every month than Germany and Japan had produced artillery shells of all types combined. General George Patton had been correct when he wrote that armies would need to devise new methods of warfare once proximity-fused artillery became widespread. The assumption that soldiers in trenches or foxholes were safe from artillery fire had been fundamental to military tactics since World War I. The proximity fuse shattered that assumption. Defensive positions that had been considered adequate protection against artillery were now death traps. Armies would need to disperse more widely, dig deeper fortifications, and move faster to avoid artillery barrages. The tactical changes forced by proximity-fused artillery rippled through military doctrine for decades. Section T operated on an accelerated timeline that would have seemed impossible in peacetime, from the initial assignment in August 1940 to the first combat use in January 1943 was less than 2.5 years. During that time, TUV's team had solved problems that had stumped scientists in multiple countries for more than a decade. They had developed miniature ruggedized vacuum tubes that could survive forces no civilian electronics had ever faced. They had designed circuits that operated reliably under conditions of extreme vibration, temperature variation, and electromagnetic interference. They had created manufacturing processes that could produce complex electronic devices at scales previously thought impossible. And they had done all of this while maintaining absolute secrecy that prevented enemy intelligence from learning what they were building. Dr. Merle Tuve never received public recognition for leading the development of the proximity fuse. During the war, the project remained classified until after Japan surrendered. Even after the war ended, Tuve was reluctant to discuss his role. He understood that Section T had solved an engineering problem that saved thousands of Allied lives. But he also knew that many people at many organizations had contributed to that success. The proximity fuse was not the work of a single genius. It was the product of systematic collaboration between physicists, engineers, manufacturers, and military personnel across dozens of organizations. Over 22 million proximity fuses were produced during World War II by more than 100 manufacturers. That scale of production required contributions from thousands of people, most of whom never knew what they were building. After the war, Tuve returned to the Department of Terrestrial Magnetism at the Carnegie Institution and served as its director from 1946 to 1966. He continued research in geophysics and radio astronomy. In 1948, he was named an honorary commander of the Order of the British Empire for his service to the Allied cause during the war. President Harry Truman awarded him the Presidential Medal for Merit. But Tuve rarely spoke about the proximity fuse. When asked about his wartime work, he emphasized the collaborative nature of the project and the contributions of the engineers and technicians who had solved countless technical problems that made mass production possible. Dr. Merle Tuve died on May 20, 1982, at the age of 80. His obituaries mentioned his contributions to geophysics and his leadership of the Applied Physics Laboratory during World War II, but most did not detail the specific work he had done on proximity fuses. The technology had been declassified for decades, but it remained obscure outside military and technical circles. Tuve himself had never sought publicity for his wartime work. He believed that scientific achievement should be measured by results, not recognition. The proximity fuse had saved lives and helped win the war. That was what mattered. The applied physics laboratory that Tuve founded continues to operate today as a research facility of Johns Hopkins University. It conducts work in national security, space exploration, and advanced technology development. The building in Silver Spring, Maryland, where Section T first assembled proximity fuses in 1942, no longer stands. It was demolished decades ago and replaced by commercial development. There is no memorial marker at the site. Nothing identifies it as the place where one of the war's most important technologies was born. The workers who assembled proximity fuses in factories across America went back to their peacetime jobs when the war ended. Most never learned exactly what they had been building. The soldiers and sailors who benefited from proximity-fused ammunition rarely knew the technical details of how the fuses worked. They just knew that anti-aircraft guns were suddenly much more effective and artillery barrages were far more lethal. The technology remained mysterious, even to the people whose lives it saved. The 702 German soldiers killed by proximity-fused artillery on the banks of the Sauer River in December 1944 were buried in military cemeteries in Luxembourg and Germany. Their graves do not mention how they died. The military records list them as killed in action by artillery fire, which was true but incomplete. They were among the first ground troops anywhere to be killed by technology that their own scientists had declared impossible. They died not knowing that the shells exploding above them contained miniature radar sets more sophisticated than anything Germany had been able to build. They died not knowing that American factories were producing these shells by the hundreds of thousands, while German industry struggled to manufacture basic artillery ammunition. The German engineers who had declared proximity fuses impossible never understood what they had missed. After the war, American technical intelligence teams interrogated German scientists and showed them captured German documents detailing their proximity fuse research. The Germans had explored most of the same technical approaches that Section T had used. They had considered radio frequency fuses, vacuum tube designs, and miniaturization techniques. But they had concluded that the engineering challenges could not be overcome with existing technology. What separated the American project from the German project was not a difference in scientific knowledge, but a difference in engineering persistence and manufacturing capability. American industry could produce miniature ruggedized vacuum tubes in quantities of millions. American engineers could iterate through dozens of design failures until they found solutions that worked. Germany lacked the industrial base and the time to compete on those terms. British scientists who had contributed the initial circuit designs to Section T watched the American success with mixed feelings. They had solved many of the conceptual problems, but had been unable to scale up to mass production. The British proximity fuse program produced working prototypes, but never achieved the reliability and cost-effectiveness needed for large-scale military deployment. When the Tizard mission delivered British proximity fuse designs to Section T in August 1940, they gave the Americans a starting point. But as Tuve later noted, the circuit design that Section T made work was substantially different from the British design. American engineers had redesigned nearly every aspect of the fuse to meet Navy specifications and survive the brutal forces of artillery gun firing. This is how wars are actually won, not through dramatic breakthroughs or genius inventors working in isolation, but through systematic collaboration between scientists, engineers, manufacturers, and military personnel. The proximity fuse succeeded because Section T could draw on the resources of American industry, the technical expertise of academic researchers, and the practical knowledge of Navy ordnance officers who understood what combat conditions would demand. It succeeded because Western Electric and Raytheon could manufacture ruggedized vacuum tubes that no one had built before. It succeeded because factory workers across America could assemble complex electronics at scales that would have been impossible for any other nation. And it succeeded because Colonel Oscar Alfred Axelson made the decision to use the technology when it mattered most, even though he was violating direct orders by doing so. The story of the proximity fuse is the story of American industrial and scientific power at its peak. It is the story of what becomes possible when brilliant people are given clear objectives, adequate resources, and freedom from bureaucratic constraints. It is the story of innovation that happens not through individual genius, but through systematic problem-solving at scale. And it is the story of a technology that saved thousands of Allied lives and changed warfare forever, developed by people whose names are mostly forgotten today. Private Heinrich Müller survived the Sauer River crossing. He was one of the 43 wounded men pulled from the water by American medics the following morning. A piece of shrapnel had torn through his shoulder, missing major arteries by inches. He spent the rest of the war in a prisoner of war camp in France, recovering from his wounds and trying to understand what had killed his battalion. When American interrogators asked him about the artillery barrage, Müller could only describe shells that exploded in the air with no warning, that killed men in foxholes and behind cover, that made the river itself a death trap. The interrogators took notes, but offered no explanations. The proximity fuse remained classified. Even prisoners of war were not told what technology had nearly killed them. Müller returned to Germany in 1946 to find his hometown in ruins and his family scattered. He worked as a carpenter for the next 40 years, rebuilding houses in cities that had been destroyed by Allied bombing. He rarely spoke about the war, and when he did, he never mentioned the Sauer River crossing. Some memories were too painful to revisit. He died in 1991, never knowing that the weapon that had destroyed his battalion was a miniature radar set packed into an artillery shell designed by American scientists who had solved a problem German engineers believed was impossible. The tactical legacy of the proximity fuse extended far beyond World War II. During the Korean War, American forces used proximity-fused artillery shells against Chinese human wave attacks with devastating effectiveness. The same technology that had stopped German battalions in the Ardennes shattered Chinese infantry formations, attempting to overrun American positions through sheer numbers. Communist commanders quickly learned that massed infantry assaults against positions equipped with proximity-fused artillery were suicidal. In Vietnam, proximity fuses were adapted for use in defensive fire around American bases and landing zones. The fuses proved particularly effective in breaking up enemy attacks during the hours of darkness when visual observation was impossible. The technology continued to evolve, with newer versions becoming smaller, more reliable, and capable of discriminating between different types of targets. Modern proximity fuses can differentiate between aircraft, ground vehicles, and personnel, adjusting their detonation patterns accordingly. The engineering principles developed by Section T influenced countless other technologies. The miniaturization techniques used to create ruggedized vacuum tubes for artillery shells contributed to the development of portable electronics in the post-war era. The quality control procedures developed to ensure consistent fuse performance became industry standards for precision manufacturing. The collaborative model that brought together academic researchers, government scientists, and industrial engineers became a template for future defense research programs. The secrecy that surrounded proximity fuse development during the war created gaps in historical understanding that persisted for decades. Many soldiers who benefited from the technology never knew it existed. Veterans who had survived battles where proximity fuses played critical roles attributed their survival to luck or superior tactics, unaware that American scientists had given them a decisive technological advantage. The full story of the proximity fuse only became widely known in the 1980s and 90s when military historians gained access to declassified documents and could piece together the complete narrative. Educational programs at military academies now include case studies of proximity fuse development as examples of successful technology transition from laboratory to battlefield. The project demonstrates how urgent military requirements can drive rapid innovation when resources are properly allocated and bureaucratic obstacles are removed. It also illustrates the importance of manufacturing capability in modern warfare. Scientific knowledge alone is insufficient. Success requires the industrial capacity to produce complex technologies at scale while maintaining quality and reliability. The human cost of technological superiority is rarely calculated in precise terms. How many Allied soldiers survived because proximity fuses destroyed enemy aircraft before they could drop their bombs? How many ships remained afloat because kamikaze attacks were intercepted by proximity-fused anti-aircraft fire? How many infantry assaults succeeded because German defenders were eliminated by proximity-fused artillery before they could organize effective resistance? The numbers are unknowable, but the impact was substantial. Conversely, how many German and Japanese soldiers died because their nations lacked the industrial capacity to develop similar technologies? How many young men were sent into battle with inadequate weapons and equipment, casualties of industrial warfare that their countries could not win? The proximity fuse represents both the triumph of American innovation and the tragedy of modern warfare, where technological disparity determines outcomes as surely as courage or tactics. The factories that produced proximity fuses during the war have long since converted to other purposes or been demolished entirely. The Crosley Corporation plant in Cincinnati that manufactured 5.2 million fuses closed in the 1960s. The Western Electric and Raytheon facilities that developed ruggedized vacuum tubes have been repurposed for modern electronics manufacturing. The physical infrastructure of proximity fuse production has vanished, leaving only archival records and museum displays to document what was once the largest classified manufacturing program of World War II. Survivors of the Battle of the Bulge, who witnessed proximity-fused artillery in action, carried memories of its effectiveness for the rest of their lives. Veterans interviewed decades after the war described the distinctive sound of airbursts and the devastating impact on German formations. Some remembered the psychological effect on enemy soldiers, the growing reluctance to advance when proximity-fused artillery was falling, the reports of German troops refusing orders rather than face weapons they could not understand or evade. The technological arms race that proximity fuses exemplified continued throughout the Cold War and beyond. Each new weapon system prompted development of countermeasures, which in turn drove further innovation. The miniature radar sets packed into artillery shells in 1942 evolved into sophisticated guidance systems for precision-guided munitions. The engineering challenges that seemed insurmountable to German scientists in 1943 became routine problems with known solutions by the 1960s. The story of the proximity fuse reminds us that warfare is ultimately decided not by bravery or determination, but by industrial capacity and technological innovation. The German soldiers who died on the banks of the Sauer River were no less courageous than their Allied counterparts. They were simply outmatched by an industrial system that could produce weapons their own nation could not replicate. Private Müller's survival was not a reward for superior virtue. It was an accident of trajectory, a matter of inches that separated life from death when shrapnel filled the air above the river. The engineers and scientists who developed the proximity fuse never met most of the soldiers whose lives their work saved. They worked in laboratories and factories, solving abstract technical problems without seeing the battlefield consequences of their success or failure. Yet, their contributions were as critical to Allied victory as any infantry assault or naval battle. The proximity fuse demonstrates that modern warfare is won as much in research facilities and manufacturing plants as on traditional battlefields. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now and don't forget to subscribe.